Hello, it is raining torrentially outside. I'm not sure if you can hear that or not, but we are going to go quickly solve, I think, 5 problems, actually 6, 6 non-homogeneous first-order systems of differential equations. So question 1, we have a 2 by 2 matrix with some complex eigenvalues and a corresponding complex eigenvector, and we're told that it has one solution given by that x of t there. That would be our particular solution. And all we're doing now is finding the rest of the general solution, which is the characteristic solution that we are going to get by expanding out v1, which they tell us is 1, -1 minus I, multiplied by e to the lambda 1, which is -2 plus I, t. And we can expand this into its real and imaginary parts by replacing this exponent up here. We will have -2 t and e to the it, like that. This e to the it will turn into a cosine t plus I sine t, and we're ready to write out our characteristic solution. So x c of t is equal to c1 times the real part of this guy up here, and we're going to get a real value when cosine is multiplied on the top, when cosine is multiplied to this -1 on the bottom, and when sine is multiplied on the bottom, like so. So we will have cosine t, and I'm a little cramped for space, so we might have to zoom in here. Cosine of t on top, and then on the bottom minus cosine of t plus sine t, because we'll have -I squared sine t, which is positive sine t, e to the -2t plus c2 times the imaginary part minus the I. We'll get imaginary values when sine is multiplied on top, cosine is multiplied to the I on the bottom, and sine is multiplied to the -1 on the bottom. So that gives us sine t up top, negative cosine t, and negative sine t, and e to the -2t has to, be in there somewhere. And all we have to do now that we have xc to make our x of t is to add in xp, our x particular solution, which is 1 to e to the -2t. And that should be it. We just have to find it in these examples here. And it looks like B is our correct answer. 20, we have a matrix with eigenvalues given and corresponding eigenvectors. We are solving this initial value problem here. So let's find a particular solution. We know that if we choose a guess for our particular solution, it has to be in the form of whatever we've added on here, this f of t term, the non-homogeneous term. And so we're going to guess it is a, b, e to the 2t. Just some constants, because that's all we have here. We have 1 times e to the 2t and -2 times e to the 2t. And thankfully, we don't have to multiply anything by t, because we don't have any overlap with our characteristic solutions, because our eigenvalues are 1 and -1, and not 2, which would be a little bit of an issue for us. So let's find x particular guess prime. That's 2a, 2b, e to the 2t, and we can plug both of these into here to find our values for a and b. Because there's an e to the 2t in every single term, I'm going to divide it out ahead of time. So we'll plug in for x prime 2a, 2b, is equal to 2, negative 1, 3, negative 2, multiplied by AB plus 1, negative 2, because we're dividing out that e to the 2t. Turning this into two individual equations, we see that 2a is equal to 2a minus b plus 1, and that 2b is equal to 3a minus 2b minus 2. Rearranging this first equation, we see that b is equal to 1, and because b is equal to 1, we can take the 4b that we had here and replace it with 4, add our 2 over, and see that a is equal to 2. So our x particular of t is actually 2, 1, e to the 2t. So we can get rid of all of this and go and solve for our c1 and c2 with our initial conditions, because our x of t right now is in the form c1 v1 e to the t, that's lambda 1, plus c2 v2 e to the lambda 2t, plus our x particular. So that is 2, 1 e to the 2t. Plugging in plugging in 0 for t, and then plugging in 4, 5 for x of t, we can solve and see that 4, 5 is equal to c1, 1, 1 plus c2, 1, 3 plus 2, 1. We can subtract this 2, 1 over here and get 2, 4, and then turn this into a little augmented matrix, 1, 1, 1, 3, 2, 4, like that. We can subtract row 1 from row 2, get 0, 2, 2, simplify this row to 1, 1, subtract it from the top row, and we see that both C1 and C2 are equal to 1. And they are looking for x of t. Well, that's just going to be, x1 of t, where x is composed of x1 of t on the top and x2 of t on the bottom. So we can just grab the top coefficient up here and say that x1 of t is equal to e to the t plus e to the negative t plus 2 e to the 2t. So looking for that. Yep, there we go. Not question D. Option D is our correct answer. 18. Which of the following is a solution to this non-homogeneous first order system of differential equations? In this case, usually what we would go do is check to see if e to the negative 2t has any overlap in our solution to the characteristic equation. But at this time, I'm actually not going to, and I'll show you why. Namely, none of our answers are multiplied by t. If anything was multiplied by t in there, we would know that even if one of the answer choices had a t, and then we know that there would be some chance that there is overlap there, and we need to multiply by t to get away from it. But because we see nothing there, we're just going to skip that. And that's just a little kind of thing that can save you, I don't know, that probably saved us 3 minutes, and now I've been talking about it for almost 1. So let's get going. We can guess that our particular solution is in the form ab e to the negative 2t, which means that x prime of our guess for our particular solution is negative 2a, negative 2b e to the negative 2t. Plugging that in for everything and remembering that since there's an e to the negative 2t term in everything, we can get rid of it. We will have negative 2a, negative 2b is equal to 1, 1, 4, negative 2 multiplied by ab plus 4, 0. Turning this into a system of two equations, we have negative 2a is equal to a plus b plus 4, and negative 2b is equal to 4a minus 2b plus 0. Subtracting an a over here, and why not? Let's subtract a b too. We can add 2b over here and see that 4a is equal to 0, so a is equal to 0, which means that this equation just simplifies down to b is equal to negative 4, and that makes our lives a lot easier because we are done. We can take our ab up here, replace it with 0 and negative 4, and see that this is just x, not c, xp of t. We can get rid of all of our guessing and everything. Although I'm actually not going to, because I do publish the PDFs for these. Whoops. And this is just our answer. 0, negative 4 times e to the negative 2t. 8, let's find the particular solution to this thing. It's probably getting pretty old at this point. Because we're dealing with solutions of our characteristic equation that involve e to the some power of t, and we know that we will not get e to the 0 of t, especially not in this case, because the determinant of this matrix is not 0, so 0 is not an eigenvalue of that matrix there. We are safe in guessing. AB. The derivative of this is just 0, 0, and we can plug both of these in and get to solving. So 0, 0 is 0, 1, 1, 0 times AB plus, nope, it's minus 2, 3. And before I expand things out, I'm going to move this 2, 3 over to this side. 2, 3, like that. Okay, we can rewrite this as 2 equals b and 3 equals a. Well, that works out really nicely, doesn't it? And we can go up here to our x particular, which is now just xp of t, because we've officially found it, and that will be 3 and 2. So our answer is A. Let's find the general solution of this thing. So a little more complicated here in that we have two different types to deal with. We have constants and e to the negative t's. So we're going to have to run two different computations to find our values for these, because really we can split our guesses up for this into ab e to the negative t plus c d. And you could go through and do that all at once. I'm not going to. It feels really out of control, at least for me. So we're going to do this one at a time. Let's make sure that t is equal to -1 is not an eigenvalue of this matrix here. If we plug in t is equal to -1, sorry, lambda is equal to -1, we will end up with 3, 1, 1, 0, whose determinant is not 0. So we're good on that front. We don't need to multiply anything up here by t. So running with this e term first, I'm going to get rid of our cd. xpg is that guy. x prime pg is -a, -b, e to the negative t. And since we're pretending that this 1 does not exist for now, it's just completely non-existent. We have a 0 e to the negative t in its place. We can just divide out the negative t's from every term, because there'll be no term without a negative t, e to the negative t in it. So plugging things in, -a, -b is equal to 2, 0, 1, 1, ab minus 6, 0. This is -a is equal to 2a minus 6, and -b is equal to a plus b plus 0. Subtracting here, you'll have minus 3a, whoops, minus 3a, there we go, or 3a is just equal to 6, a is equal to 2. Subtracting this b, negative 2b is equal to 2, so b is equal to negative 1. So we can go up here and replace our a with a 2 and our b with a negative 1. And that is half of our job done. Now we have to go and remember that we still haven't found the contribution to our x particular of this 1 here. So this is actually xp of t. Now xp g, we're setting up a new one. That's just going to be ab, some constants where x prime is just 0, 0. And plugging this in, we see that 0, 0 is equal to 2, 0, 1, 1 times ab minus 0, 1, because we are completely ignoring the existence of the 6e to the negative t because we have already figured out its contribution to xp. Then solving this, we see that 2a, or that 0 is equal to 2a, and that 0 is equal to a plus b minus 1. So since a is equal to 0 and b is equal to 1, we can go up here and replace those. So we have plus 0, 1, like so. We are actually not done yet because, and I should have really done that at the start while we were checking whether or not negative 1 was an eigenvalue. We're looking for a general solution, not just our particular solution, unlike a lot of these other questions. So we will have to solve the homogeneous case here. We'll be solving 2 minus lambda multiplied by 1 minus lambda equal to 0. This is true for lambda is equal to 2 and 1. Plugging in lambda equals 2 into a minus lambda I, we get 0, 1, negative 1, 0, and we get an eigenvalue of 1, 1 out of that deal because it says x1 is equal to positive x2. Then next, for lambda equal to 1, we get an a minus lambda I of 1, 0, 1, 0. We can simplify that down. x2 is free, and this is saying that x1 is equal to 0, x2 free, and so our eigenvector is 0, 1. And so overall, I can get rid of or move around some of this work for here, just get it out of the way. Overall, we can go up here and add to our solution by saying that xc is equal to c1 v1, which is 1, 1 e to the 2t plus c2 v2 e to the 1t. And then x of t is just xp plus xc, so 2, negative 1 e to the negative t plus 0, 1 plus c1 1, 1 e to the 2t plus c2 0, 1 e to the t. And we're done. And since this question is a short answer question from my professor's, Dr. Progotanyan's practice questions, it's a short answer question, so this is our answer. 20, the only time they have mentioned the existence of the fundamental matrix in the past 3 years in an exam was in 2017, and it was question 20 on that exam. We see that phi of t is given there. It's a fundamental matrix of this homogeneous system, and we are trying to find the particular solution of this non-homogeneous system. So xp of t, when we're dealing with a fundamental matrix here, is given by phi of t times the integral of phi to the -1 of t times this function here that we have added on. I'll call that g of t dt. And if we solve this, we will have our solution. So we already have phi of t. We're going to need phi inverse of t. So that that will be, let's see, phi of t is equal to e to the t, negative e to the t, e to the 3t, e to the 3t, and phi inverse of t is going to be 1 over the determinant of phi, so that's 1 over, let's see, we'll have e to the 4t plus e to the 4t, so 2e to the 4t, multiplied by the matrix where we exchange the a and d positions, so e to the 3t, e to the t, and flip the signs of the remaining positions, so e to the t, negative e to the 3t. Okay, now we're taking this guy and multiplying it by 0 for e to the t on the right, taking the integral dt, but actually I won't write that just yet. Okay, so this is equal to, well, let's do the computation. We have 1 over 2 e to the 4t on the outside. We're going to get a 2-by-1 matrix. Our first entry will be multiplying our first the first component of the first row with the first component of the first column, and then these two, adding the sum of those two, the product of those two, we get negative 4 e to the 4t. That took me a second, and then 4 e to the 4 e to the 2t, like so. Dividing out our 2e to the 4t from all of these terms, we will get 2e to the negative 2t here and negative 2 there. So that is that, and we are now taking our integral of negative 2e to the negative 2t dt, and in fact we'll be leaving out the constants that we would normally get from this. I'm not exactly sure why. We get negative 2t minus e to the negative 2t. And then this, in turn, is being multiplied by our original fundamental matrix. We'll get a 2-by-1 matrix composed of negative 2t e to the t minus e to the t, and then 2t e to the t minus e to the t. We can factor out an e to the t, and we'll be left with xp of t as negative 2t minus 1, 2t minus 1, all multiplied by e to the t, and that is option D, which is correct. Okay, yeah, we're done. These problems are actually a lot scarier than I originally thought they were, and I hope you think so too.